So uh, we'll wait for I think 2-3 more minutes. Let others to join,
No
and then
problem.
we can start.
No problem.
Yeah.
No problem.
Could you mute your mic, Arumugamji?
Okay.
Hello, Ashwini. Am I audible to you? So in the meantime, let me talk to Kartika and Ashwini. So you can type in the chat box if you're not able to speak. Have you people gone through the classes of previous weeks, week 1 and week 2, and solved the solution? Like solved the assignment or not? Or went through the videos, YouTube videos, or the assignment solution or the PPTs that I have provided? Hello? I mean, you can type in the chat box if you want. We'll start at 3:05:35. In the meantime, I'm just trying to figure out so that if I am going to take forward something, you guys should not miss anything. So the point is this.
Yes, sir. I will done my assignment.
You've done?
I done assignments and
Okay.
submitted.
Assignment 1 and 2, right?
Yeah, sir. One and two.
Okay. And what about you, Ashwini? Okay, no problem. So we are waiting for 2 more minutes and then we can start. First of all, I'll give you a flashback of week 3 classes, what Professor Tomar has taught in case you have not gone through week 3 classes. And then I have made certain questions on the basis of week 3 classes and I'll provide a solution. We will discuss about it. So the point is this key. Um, this is my email. In case Ashwini you don't have it, please note it down. sd19ip011 at the rate isocol.ac.in, and you can anytime contact me. So I guess I'm sharing in the drive the combined PDFs of Professor Tomar also, where all the lectures combined PDFs are there, and you people have to go through it. So as we know, in the week 2 class, we stopped at the point of nuclear isomers. What are nuclear isomers, and how are they stable, and what is the chemistry behind them? Now in week 3 class, what we have done, so we are starting a flashback. So Professor Tomar has taught about the energetics of various decays. What are the decays? Alpha, beta and gamma decays. So I will be sharing this document. This is the combined document of week 3 class. Here what happens, if you see about the energetics of the alpha decay, so if we have X, which is atomic number and mass number, when alpha particle is emitted, which is doubly charged helium ion, this is what finally happens, that atomic number gets changed by 2 and the mass number gets changed by 4. We already know it. Example, uranium, when emit a doubly charged helium ion, it changes into thorium 234. Now how do we calculate the Q of it? So in order to calculate the Q, what we do, we sum the reactant minus product into C square. So E equal to mc square we know, and here m is delta m. Delta m means mass of the reactant and mass of the product. So what happens if you see m of 238 U, which is atomic number will be 47.308, and then we have thorium 40 and alpha is this. We multiply it and multiply it with c square, which directly gives us a energy, and delta m is m minus a c square. So q alpha is shared between alpha and thorium in inverse ratio of their masses. So professor has taught it. Please go through the video. If you have any doubt, then come back to me. Like this is how the energy of alpha and the energy of the emitter are related, along with the kinetic energy comes into the picture, and then how does that alpha decay happens, and the counts, like which are forbidden, which are possible, how many times it can continue. It is all being explained in the video. Okay, now professor has talked about the half-life and alpha energy. Why is alpha decay not observed in low and medium A nuclei, and why this energy while going down from thorium to radium to polonium, this energy, alpha energy, is getting decreased and the half-life gets increased. So this is directly related to this B by A cross A plot, which we have already gone through in the previous classes. If you have any doubt, please go through the week 2 classes. Okay, so then Professor Tomar in later sections talked about the Geiger-Nuttall law, where he has provided a relationship which is log lambda equal to A log R alpha plus B, where A and B are local constant, and the log lambda versus log R alpha is different for 4n, 4n plus 2 and 4n plus 3 series, and it is correlated as R equal to P e raised to Q. I know if you have not gone through it, still you will not be able to understand everything, but I'm just giving you a quick flashback, because when I will discuss the assignment, in that case, even if you have heard that okay, there is some term like Geiger-Nuttall law or Q alpha or delta mc square we do, at least you will be able to understand something. Then in later time, if you will see my video, which is I'm going to upload on YouTube, or see the solution or see the professor video, you will be able to understand at least, because I cannot explain everything because I have to discuss the assignment, but I just give a quick flashback in order to give some a proper prior understanding what we are going to discuss now. Then again, professor discussed the Coulomb barrier for alpha emission and how this ergs is related to Joule, and what is the classical energy and why it cannot escape from a potential well of 238 U with a Vc of 23.2 mega electron volt. So quantum mechanically, the alpha particle can penetrate a potential barrier with a finite probability. So quantum mechanically also, their alpha particle has all the penetration mechanical behavior for penetrating the potential barrier. So please go through it, and please remember this relation in between E square per centimeter, which is ergs, to joules, and how they are correlated, and how do we calculate the Vc, Z1 Z2 E square over R1 plus R2. So go through this, and this I will anyway share a document, and then there is this penetration of potential barrier, and what are these all terms, this all they have explained. We are going for a little bit advanced now, so until unless we will not do question, we will not be able to understand. I'm just showing you a flashback. So then there is a comparison between calculated and experimental lambda values, and which are not very difficult, but there is a remarkable success in predicting the lambda values by using these equations. Okay, now then there is a hindered alpha decay, which transition are allowed, which transition are forbidden, centrifugal barrier for EE nuclei, for odd nuclei, for even nuclei, for odd even nuclei, what is the hindrance factor, and what is the alpha preformation probability, and how these calculated lambda values are greater than experimental values. All this has been explained in the videos. Okay, now there is a systematics alpha decay, like how does it happen. Now isotopes and isobars, they have talked that polonium, radium, thorium, how this is changing the E alpha along with atomic number, so atomic mass. So please go through it. Then there is a systematic alpha decay, how this shell effect is actually modifying it, and daughter nucleus which have mass number, which they have large E alpha, which have mass number not a magic number, they have small E alpha. And why does it happens, we have already which is already been explained in the previous classes. This was the class 1 of week 3. Then he has talked about beta decay. I'm now going a little bit quicker. What happens in the beta decay, we know there is a change of delta Z when there is beta minus decay, which is a beta decay plus 1, and there is no change of A, which is delta A equal to 0. Now when there is a positron, which is, or you can say electron capture, delta z equal to -1 and delta a equal to 0. So what is the threshold of beta plus decay? Now in beta minus decay, what happens? Suppose we have an element x with a z, it gets converted into a y z plus 1 plus beta minus or mu bar. Now there could be a neutrino or there could be an anti-neutrino. Now what is it? When does the electron capture happens? What is the energy of it? Similarly, the way we have calculated for the alpha particles, we calculate for the beta particles. Now there is the analytics of beta decay, why it is a continuous spectrum. Now do they follow the conservation of mass and energy? Do they violate it? How do they violate it? And till when they are going to continuously decay, and when they are going to stop, and how do we predict it? These are being explained into this. So then there is neutrino hypothesis, that emission of another particle which is neutrino along with beta particle which is mu, or anti-neutrino which is mu bar. So properties of neutrino are like this: spin is half, charge is 0 and mass is 0. So n is giving a p plus electron plus neutrino. Okay, so discovery was in 1956 by Fred Wren and George Cowan, and experimentally in a nuclear reactor, triple coincidence between n and 2 511 kilo electron volt gamma photons happens. So I know if you have not seen the video, you will not be able to understand a lot, but yeah, just remember there is a neutrino hypothesis. There is something like neutrino which gets emitted along with a beta or positron when a beta decay is happening. Just remember this for time being. Now then he explained the Fermi theory, that does the electron emitted in beta decay come from the nucleus, or it is coming from somewhere else. So this is what I was talking about, that beta is created during conversion of n into p, which is beta minus, or that of a bound p into n b positive. Now which is n is giving p plus electron, it gives an anti-neutrino, while when p goes back to n, it gives a neutrino. So the lambda that we calculate is around 10 raised to power minus 12 meter, which is much larger than a nuclear dimension. So then there is a Fermi golden rule, that what is the probability that an electron emitted with momentum pe and pe dpe, you will be able to find it. So now then he has evaluated it by using certain equation. These equations are there, please go through them. Then there is a Coulomb correction factor into this, and then you get the final Curie plot. Now in this Curie plot, this is the testing of Fermi theory by comparing experimental momentum spectra with the predictions. Then comparative half-lives for beta decay and selection rules of beta decay, similar to the alpha decay. The electron and neutrino are emitted with anti-parallel spin. Here it should be s equal to 0, and electron and neutron are emitted with parallel spin. Fermi selection rule is there, Gamow-Taylor selection rule is there, and allowed action are when L equal to 0 and delta pi is equal to no. So L plus S equal to II minus IF to II plus IF. If you have not understood it, we will discuss the assignment, no problem. Please stay here. I'm just giving you a quick flashback what he has taught. So suppose we consider certain cases. In this case, delta L is there, L is there, delta pi is there, and log ft is there. Now how, when, which is feasible, which is not feasible, which is allowed, which is not allowed, we can see here. Delta pi should be no, log ft is here, L should be 0, this should be 0. So allowed or super allowed are this. Okay, as the log ft is increasing, or delta pi is yes, this becomes forbidden. And then if this is much more, and L is also not 0 and delta L is also not 0, then it is completely forbidden. Okay, so which are forbidden, which are not, please go through them. Then the quark structure of nucleons, as we know, UUD or UDD, why a electron has a -1 charge, why a proton has a +1 charge, why neutron is neutral, and why beta decay is a weak interaction and short range, and they have very large masses. It is being explained very well. So please go through them. The quark one. Now similarly, he has explained the gamma decay, the range of half-life, the energy, and the Vyskov theory. Gamma ray carry integral units of angular momentum, remember it. And now there are certain rules of gamma decay also. So L equal to 1, L equal to 2, L equal to 3, L equal to 4, change in angular momentum and parity. So please go through the videos and then go through all these slides. I will share this PDF. Then there is a decay scheme of cobalt 60. Gamma decay constant is being calculated, And then there is a decay constant for electric multipole. I know it's a lot of stuff I'm telling you in one go, but I need to tell you because we are going to discuss the assignment. I will explain it in detail what will be there in assignment, but I cannot explain everything in detail here. Just to tell you that there is a decay constant for electric multipole for a gamma decay, which is according to the Vyskov single particle estimation of tau. Now what is it? Why does it correct a collective motion? What is there? How does it happen? You have to see the video. It is something like there. I'm just to tell you. Then there is internal conversion. What is the lifetime of internal conversion? What is a hindered gamma decay similar to hindered alpha and beta decay? All this you can go. Then nuclear isomers. Now then after that there is a concept of ionization radiation and how they are interacting with the soft matter. So if we distribute the ionizing radiations, they could be heavy charge, they could be light charge, they could be electromagnetic radiation, or they could be neutral. Example, for heavy charge are alpha, light charge are beta, electromagnetic radiation are gamma or x-ray, and neutral particles are neutrons. And then there are certain sources. For light there is Auger electrons, and for electromagnetic radiation there is Bremsstrahlung. When a radiation falls on a material, the material, like a balloon, it splits, and it gives some radiation outwards. Now depending on the radiation it is giving outwards, these ionizing radiation which are visible to the human eye, they can be classified into certain categories. These are the categories. Okay, now radioactivity in the environment, then type of radiation, level of radiation, what is the need of radiation detector, and how do we make the radiation detector. So these all are being explained. And then heavy charge particles, what is the difference between ionization and excitation, and what should be the velocity when this high accelerating particle gets stopped, and when does it get not stopped. Fractional energy losses and all this have been explained very well. So please go through all the videos, especially the Bragg curve. And one more important thing is there. This is the last lecture where he has actually talked about, just a minute, yeah, collisional energy losses. What happens when there is a collision happening? So there is a radiative energy loss for high atomic absorbers, high atomic number absorbers. Why does it happen? And total energy loss is calculated by these equations. So please go through them. Then this is Bremsstrahlung, which is acceleration and deceleration of an electron in the electric field of a nucleus. So the probability of radiation emission is 10 raised to the power 6 times more than electron than that of protons. Why is that so? That why do you find the radiation emission more for electron than the protons? It is being explained in terms of intensity, and this is how this equation is coming. Please go through the video. And then this is a range. How do we calculate the range? And at last he has talked about interaction of positrons. So difference with electrons is upon thermalization, positron annihilates with an electron. Positron annihilation emission of 2 gamma photons, each of energy 511 kilo electron volt. And then thermalized positron can also form positronium atom with electron. Can a nucleus be made only with a positron and electron without a proton? It is also a question. So it is completely on the positronium chemistry, which is a completely different branch of chemistry, which will be told in detail in the coming lecture. So yeah, just a minute. So I know I have said a lot of things. Just to give a quick flashback, what we have learned till now, we have learned what is radioactivity, how many types of radiations are there, then the kinetics of them, and then the energetics of them, then the quantum mechanical explanations of them. And now we are going slowly towards the radiation detection, the chemistry of radiation detection, how these radiation can be detected. Now there are certain questions on the basis of week 3 classes which will help you in solving the assignment. So let us go to the question one by one. Okay, so yeah, now everybody is here. The first question is saying, in an alpha decay, the kinetic energy of alpha particle is 48 mega electron volt, and Q value of the reaction is 50 mega electron volt. The mass number of the mother nucleus is X. Find the value of X by 25. Assume that the daughter nucleus is in the ground state. And the options are 2, 4, 6, 8. Just for a hint, I am telling you Before proceeding with our solution, let us discuss the various terms we will use. Alpha decay, it is a radioactive decay in which a nucleus emits an alpha particle, which is nothing but an ionized helium nucleus, and thereby transforms into a different atomic nucleus with a mass number that is reduced by 4 and atomic number that is reduced by 2. Now, what is the Q value? The Q value for a reaction is the amount of energy absorbed or released during a nuclear reaction and can be determined from the masses of the reactant and product. Q value affect the reaction rates. The formula that we are going to use here are K alpha equal to md over m alpha plus md dot q. We have the value of kinetic energy of alpha particle, Q value of the reaction we have, mass number of the mother nucleus x we have to find, and then we have to tell the value of x by 25. Will you be able to solve it? Anybody? Hello? Anybody is there? Arumugam ji, Kartika, Ashwini. Anybody is there? I mean, if you are not able to solve it, I'll definitely show the solution. But did you understand the question, or should I repeat the question? You can type in the chat box. You can type in the chat box if you want. What is the question saying? There is an alpha decay whose kinetic energy is given. Q value of the reaction is given. Mass number of the mother nucleus is x, suppose, and they are asking us what is the value of x by 25. That is the question. I am giving you a hint. The hint is that what happens when an alpha decay is there, and what is the Q value, and what is the formula that we are going to use here. Okay, I will explain. No problem. I mean, these questions are there in your assignment also, so they are not the exact questions, but these questions will definitely help you in solving the assignment. Some of them are exact also. So let's see what is the answer. So as we know that the alpha decay causes changes in the atomic number and mass number of the mother nucleus mathematically, which is shown as like this. Yeah, like this. Suppose you have a nuclei A with atomic number Z and mass number Y. When there is an alpha emission happening, it converts into V, and change of atomic number is 2 and the mass number is 4, where A is a mother nucleus and B is a daughter nucleus. Now helium is the alpha particle and subscript denote atomic number and mass number, we very well know. Now we know the relation between the kinetic energy of alpha particle and the total energy of the reaction, which is given as K alpha equal to md over m alpha plus md dot q, where K alpha is the kinetic energy of the alpha particle, Q is the total energy change of the reaction, and md is the mass of daughter nucleus, which is B, and m alpha is the mass of alpha particle, which is this. Now let's see. What are we given? We have been given that the kinetic energy of the alpha particle, which is K alpha, is 48 mega electron volt. Now total energy change in the reaction is 50 mega electron volt. As we can see, the kinetic energy of alpha particle was given to us as 48 mega electron volt, and Q value of the reaction is 50 mega electron volt. What is Q? Just a minute, somebody is trying to join, I guess. Okay. So Arumugam Raman, are you the same person? I mean, okay. Arumugam ji, are you able to hear me? I'm explaining the answer of the first question of the assignment.
Yes, sir. Yes. Yes, yes, I can hear you. I connect with my desktop, sir.
Okay, okay, no problem. So as we can
Okay,
see,
thank you.
I'm just zooming it if you are not able to see. So we know what happens when there is alpha and beta emission. Now let's see. Now let's see what is happening here. So this is the equation K alpha equal to md over m alpha plus md dot q, where K alpha is the kinetic energy of alpha particle, Q is the total energy change, and md is the mass of daughter nucleus, and m alpha is the mass of alpha particle. We have been given that the kinetic energy of alpha particle is 48 mega electron volt and Q value of the reaction is 50 mega electron volt. Suppose the mass number of mother nucleus is what? Mother nucleus is this. Suppose the mass number of mother nucleus is x. Now we have to tell you the value of x by 25. Now let's see. So kinetic energy of alpha particle is 48 mega electron volt and the total energy change in the reaction is 50 mega electron volt. From the reaction of alpha decay of a mother nucleus given above, we can say that mass of the nucleus will be x minus 4, right? If you consider it x, now if the mass is x, the daughter nuclear mass will be what? X minus 4. Am I right or not? Because the alpha particle mass is 4, we know that, because 4 is getting subtracted from y, so y minus 4. So if suppose the mass number of the mother nucleus is x, okay, let me write it like this, just a minute. Suppose mother nuclei has mass equal to x, so the daughter will has what? X minus 4. We know it very well because the alpha emission is taking place. Now what is happening? Substituting the values to the given equation, substituting the values, md means x minus 4, which is the mass of a daughter nuclei, x minus 4, and m alpha plus md, m alpha is x minus 4 plus 4, which is mass of daughter plus mass of alpha, which is x. So this is 48 mega electron volt and Q is 50 given to us. Now putting the values, x minus 4 over x equal to 48 over 50, the 50 will go here. Now taking the x here, it becomes 50x minus 200 equal to 48x, 2x equal to 200, x equal to 100. Now we have to find the value of x by 25, that means 100 by 25, which is 4. So the correct option is B, which is 4. Again, I'm asking, is there any doubt in this question?
No, sir, it's okay.
Let me ask one by one. Okay, so Kartika has no doubt, I guess. Arumugamdi, you were able to understand what is kinetic energy, what is Q, and now what happens when there is an alpha emission. We were given the kinetic energy of an alpha particle and the Q value, and we were being asked that what will be the final value of this. So this is what being asked. So did you understand the question and answer?
Hmm. Hello.
Yeah, yeah.
No, sir. No understand, sir. I will read again the video.
Okay, just a minute. It's not a tough question. I mean, I'm just giving you a
Okay.
quick check again. There is an
Okay, sir.
what happens when there is an emission? Could you mute Arumugamji? Yeah. So what happens when there is an alpha emission? Alpha emission is nothing but a doubly helium atom. This is an alpha particle. This is a parent. This is a daughter. Now, when alpha emission is happening, there is a change of 4 in the mass number and 2 in the atomic number. Now this is an equation which correlates the kinetic energy with Q with the mass of daughter and mass of alpha. Now what is Q? Q is the total energy change of a reaction. What happens? Q value of a reaction is the amount of energy absorbed or released during a nuclear reaction and can be determined from the masses of reactant and products. Now this is the equation there. Now the question is saying that in an alpha decay, kinetic energy of alpha particle is 48 mega electron volt and the Q value of the reaction is 50 mega electron volt. The mass number of mother nucleus is x. If you suppose, which is y here, suppose this is mother nucleus and the mass number is, instead of y it is x. So the daughter will be x minus 4, right Arumugamji?
Yes, yes, sir.
So
Yes, sir.
okay, so this is what is there. Now they have given us certain values. The kinetic energy of alpha particle is this, Q of the reaction is this. So the mass of the daughter nuclei will be x minus 4 and the alpha particle we know it is 4. Now we just substitute the value into this equation. So if we are substituting the value into this equation, md is x minus 4, m alpha plus md, which is 4 plus x minus 4, 48 is the k alpha and q is given to us as 50. Now cross multiplying, it becomes x minus 4 over x equal to 48 by 50. From here the value of x comes out at 100. Now question was asking that what will be the final value of x by 25. Now when the x is 100, the x by 25 will be 100 by 25, which will be what? 4. That's it. What was to learn from here? What is Q? What happens in alpha decay? What is kinetic energy? What change takes place in atomic number and mass number, and how the kinetic energy related to the total energy, and how do we calculate the x? This is all. There are one or two questions in your assignment similar to this kind of question. You will be able to solve now. Am I? This question is clear, Arumugamji? Am I clear to you?
Yes, sir. Yes, sir.
Okay.
Clear, very clear, sir. Very clear. Thank
Okay.
you, sir.
Great. So this is a question with answer. So I this is a question of the assignment only. Neutrino hypothesis in beta decay can explain what? Now I guess you people have not gone through the video, so I have given the answer. Now there is a difference in the spectrum of positron और beta decay, continuous beta spectrum, conservation of parity, या फिर log ft values for beta decay. If you will go through the classes of Professor Tomer, where he has already taught the neutrino hypothesis, yeah, here in the neutrino hypothesis, if you will go in the beta decay, then you will see, okay, yeah, here. So what was there in the neutrino hypothesis? So in neutrino hypothesis, there is an emission of another particle neutrino along with the beta particle. We know that very well. Now properties of neutrino is what? It has a half spin, the charge is 0 and the mass is 0. Now mass plus energy is conserved, so QB is shared among these three particles. What are these three particles? Product nucleus, beta and neutrino. So it gives a continuous beta spectrum. Now the energy of angular momentum is conserved. So discovery of neutrino was here. This is the equation, and then the hypothesis says certain statements. Yeah, from here we derive the Fermi theory of the beta decay, and then we come to the conclusion of which particles, after all these correction factors, we come to the conclusion that which are the selection factors of beta decay. Ki what should be the Fermi selection rule and what should be the Gamow-Taylor selection rule for a beta decay. Now again I showed you this, the delta L, L, delta phi and log ft. Now this term log ft, this log ft, how much should be the value, and what is it for a super allowed, first forbidden, second forbidden or third forbidden transition. This was the actual explanation of, you know, neutrino hypothesis. So if you will go through all these video, which I am not able to explain in detail right now, you will come to know that this is a question of your second assignment. The correct answer is the neutrino hypothesis in beta decay can explain the log ft values for the beta decay. Okay, please go through it. I am not going in detail. If you have any problem, please write to me. Now let's go to the next question, question number 4 first of all, before going to the question number 3. I am also showing you the solution, but let me zoom it for a time being. Okay, so the question is saying that the nucleus X, please solve along with me. The nuclear X is initially at rest, undergoes an alpha decay according to the equation. Let me hide it for a moment. Yeah. So if I control D this, and now I'm deleting this because you need to solve it. So now you tell me. So a nucleus initially at rest undergoes alpha decay according to the equation Zx232 90 by A plus alpha. Now what is the fraction of total energy released in the decay will be the kinetic energy of the alpha particle. The question is asking simply, we have been given a compound X with an atomic number Z, mass number 232. It is giving an alpha particle. Now what is the fraction of kinetic energy that will be released? I just now solved the question. If you need a solution, I can show you. This is a solution. So we know that the equation can be represented as x z 232 gives 90 by 228 plus 2 helium 4, which is an alpha particle. Now as nucleus x is initially at rest, as the nucleus x is initially at rest, according to the conservation of momentum, 0 equal to py plus p alpha, the momentum of nucleus is y and alpha particle will be same. Now we know the kinetic energy in the momentum is related by kinetic energy equal to p square by 2m. From here kinetic energy is inversely proportional to the mass. So kinetic energy of alpha and kinetic energy of y will be mass of y over mass of alpha, because they are inversely related. So here mass is directly proportional to A. So kinetic energy of alpha over kinetic energy of y will be 228 over 4. 228 which is A here, and 4 is which is mass of alpha. So kinetic energy of alpha plus kinetic energy of total equal to 228 over 232. So the correct option is D. Again I'm saying, are you able to understand? Arumugam ji, should I repeat again?
Yes, sir. Please repeat again, sir. Thank you.
Okay, Kartika, you understood, right?
Yes, sir.
Okay, great. So yeah, you see, Arumugamji, what is happening? You know, just now the first question that we solved in this, our nucleus was initially at rest. Now, if it was at rest, the total angular momentum will be conserved, which is the sum of the momentum of the y and the alpha should be 0. Momentum, you know what is momentum? Mass into velocity. Then there is angular momentum. Okay, so what happens when it is at rest? It is conserved. Okay, now there is a nucleus x which is initially at rest and it goes alpha decay. Now when it's going alpha decay, according to the equation, they are asking what is the total energy released in the decay, which will be the kinetic energy of the alpha particle. So they are asking the ratio of kinetic energy of alpha particle with the kinetic energy, which is the total kinetic energy of the reaction. So now we know when an alpha particle is emitting, there is a change of 4 because helium atom is getting emitted. Kinetic energy and linear momentum are directly related with the equation Ke equal to p square over 2m. Because what we know, how this relation came, you know, Arumugamji, how this relation came. Okay, so kinetic energy is what? This you know, kinetic energy is 1 over 2 mv square. Okay, Arumugamji, are you listening me?
Yes, sir. Yes, I am listening, sir.
And momentum is mass into velocity. Now if you put mass into velocity into this, Ke becomes 1 by 2 into P into V. Okay, are you getting me?
Yes, sir. Yes, I am online. Online.
So
I'm
if you
getting.
see, if we are we if in this equation, if in this equation we multiply by 2m, then this will be p square. If suppose this equation, equation number 1, we multiply by 2m, okay, and we divide by 2m on both the sides, so this will be kinetic energy the right side will become 1 by 2 mv square into 2m, which will be 2 cross 2, which is m square v square, which is p square. Why? Because p equal to mb. So now the left side will become what? Left side will be kinetic energy cross 2m is equals to p square. Okay, so from here kinetic energy and momentum will be related as p square over 2m. Just a minute, let me show you again. Now you have a look over this equation, Arumugamji. We know that kinetic energy is half of mb square. Now we multiply this equation 1 with 2m on left hand side and right hand side. Now if we see the right hand side, half mb square cross 2m, this becomes m square v square, 2 got cancelled by 2 and this becomes m square by b square.
M square, V square.
Okay, now momentum is p equal to mb, so this m square v square will be p square, right? left side
Okay, sir.
left side will be kinetic energy cross 2m and right side will be p square. So the kinetic energy
P
in
square.
linear momentum is related by kinetic energy equal to p square by 2m. Okay, now see the solution. We know that kinetic energy equal to p square by 2m. So from here the kinetic energy is inversely proportional to the mass, right? That means kinetic energy of alpha and kinetic energy of y will be mass of y over mass of alpha, because kinetic energy is inversely proportional to the mass. So this is alpha, kinetic energy is inversely proportional to the mass of alpha, and kinetic energy of y is inversely proportional to the mass of y. The mass is directly proportional to the atomic number, this a mass number. We can say here that this is 232 and this is a. Okay, so we can see here m is directly proportional to a. So kinetic energy of alpha over kinetic energy of y will be m of y over m of a. Now m of y will be what? M of y will be 232 minus 4, which is 228, and m of alpha is 4. Now they are asking the fraction of kinetic energy, which is the kinetic energy of alpha over kinetic energy of total. So total is 228 plus 4, 232. So the kinetic energy ratio of fraction of alpha particle to the total kinetic energy will be 228 over 232, which is a change in their atomic masses. It is nothing. They were asking the fraction of kinetic energy of alpha to the kinetic energy of total. This is the right answer. I don't know you are able to understand or not. I cannot explain more than that.
I'm okay, sir. I'm okay. I understand. I understand.
You have
Thank
to
you.
take into account this equation. Okay,
This equation will never. Okay, okay,
and this how this equation
okay.
came, how the this equation came, I have already explained you. And then you
I will
put
notice. I will.
put the values, and then from here
Okay.
the correct answer comes. The
I
correct
will.
answer is option number D.
I will. I will notice. I will notice.
Okay.
Thank you, sir.
Okay, now the next question is saying, in an alpha particle, if an alpha particle is moving opposite to the direction of electric field, then its velocity, it will increase, decrease, it will remain unchanged, or none of these. Remember, I'm just giving you a hint. What is an alpha particle? They are positively charged particles. It is essentially a helium nucleus consisting of two protons and neutrons. Two protons correspond to 2 units of positive charge, and 2 protons and 2 neutrons correspond to 4 units of mass. The symbol of an alpha particle is 4He2. Now what happens in the electric field intensity? It is defined as a force experienced by a unit positive charge in the electric field at any point. Now the direction of electric field is taken away for the positive charge and towards the negative charge. The positive charge experiences a force in the direction of electric field, and the negative charge experiences, just a minute, and the negative charge experiences a force opposite to the direction of electric field. E equal to F by Q naught. So there are certain things. What is an alpha particle? We know. Now we know what is the symbol of alpha particle. Now what happens when there is an electric field? How the electric field and charge are correlated. Now the question is saying, if an alpha particle is moving opposite to the direction of electric field, its velocity, it will increase, decrease, it will remain unchanged, or none of these. It will increase, it will decrease, it will remain unchanged, or it will none of these. What is electric field? What is an alpha particle? What is a charge? What is the direction of electric field? Now then you answer this question. Kartika, can you answer this question?
So it's decreasing.
Okay. Arumugamji, will you try to answer the question? I'm talking from the very basics. I mean, it is more or less the same concept. We till now we know what is an alpha particle. Now, an alpha particle is moving opposite to the direction of electric field. Now direction of electric field is taken away from positive charge and it is towards the negative charge, and alpha particle is itself a positively charged particle. So what will happen when alpha particle is moving opposite to the direction of electric field, its velocity will increase or decrease. For example, let me tell let me show you in this way. Arumugam ji, suppose
Yes, sir.
this is the direction of a train, which is train is moving into this direction. Okay, and
Okay.
you are also running into this direction. Okay,
Okay.
now if you sit inside the train and you start running in
Mm.
the direction of train, so your velocity will yourself
Okay.
increase, right? But
Yes, I agree.
but if you move opposite to the velocity, then your velocity will be decreased, right?
Degrees. Yes,
Yeah.
sir. Yes, sir. In
Now
opposite direction, will degree.
now let's see the solution. The solution is, we know the electric field is this, alpha particle is moving opposite to the direction of electric field. Okay, we know that an alpha particle, it is essentially a helium nucleus consisting of two protons and neutron. It has two units of positive charge. When a positive charge is put inside the electric field, Arumugam, could you mute? Yeah. So when a positive charge is put inside the electric field, it experiences a force in the direction of electric field. Because electric field is here only, and this will try to be get attracted in the direction of electric field. Now we are moving the alpha particle opposite to the direction of electric field. Therefore, an alpha particle moves opposite to the direction of the electric field, it will experience a force opposite to its direction of motion, and therefore its velocity will decrease. Yes, Kartika, your answer is right. The correct answer is decreases. This is the same case. The train is running into this direction, but you are running into this direction but inside the train, so you are not able to overcome. That's why your velocity will automatically decrease. Are you able to understand what I am saying? Suppose there are stairs, the normal stairs on a plane surface which are running into this direction. On these stairs you are running opposite direction. So if you are running by 10 km per hour, and these stairs are going in the forward direction by 5 km per hour, your complete velocity will be only 5 km per hour, because this 5 km per hour will be reduced by these stairs. So we are have to account the term that what is the charge on alpha particle, what is the direction of electric field, and how this direction will change the velocity. Simple. These three things are there. Arumugam ji, are you able to understand? Hello. Arumugam ji, are you able to understand the question? Okay, no problem. I cannot wait. I'll move forward. So, Kartika, the next question of the assignment is, Brahms-Strahlung intensity of a charged particle varies with its mass as 1 by m square, 1 by m or m square. This is directly from the equation has been derived by Professor Tomer into his last class. So the relation is 1 by m square. You can go through the class, and if you have any doubt you can come to me. The correct answer is 1 by m square. Let's go to the seventh question. Now the seventh question I am asking about a beta emission. Let me took this again, make double, and now let me delete the answer from here. So the question is saying, Kartika, calculate the maximum kinetic energy of the beta particle. Now slowly we are going to the beta emission, the energetics of the beta decay. The calculate the maximum kinetic energy of the beta particle emitted in the following decay scheme, where 12 nitrogen is giving 12 carbon star plus electron plus neutrino, or 12 C star is giving 12 C plus gamma. The atomic mass of 12 N is 12.016813 units, atomic units. So we have to calculate the maximum kinetic energy of the beta particle. Will you be able to do this question, Kartika? Hmm?
No, sir. I
Okay.
want to read one more.
Okay, no problem. No problem. You read the question. Question is saying they are asking the magnetic maximum kinetic energy of the beta particle, which is emitted in the following decay scheme, and atomic mass of the nitrogen 12N is given as 12.018613 atomic units. Okay, let me show you the solution. No problem. Kartika, just have a look because we have one question of this kind in our assignment. You will be able to solve. Now we don't know the atomic mass. Atomic mass of 12 neutron is giving us like this, right? These are the equation in which neutron and gamma particles are getting emitted. Now this energy is given as 4.43 mega electron volt. Now they are asking the maximum kinetic energy of the beta particle emitted in the following decay scheme. Now let's consider net reaction. Net reaction will be what? This reaction plus this reaction. If we add both of them, this is the net reaction. So this and this got cancelled. When we add these two, now this becomes a net reaction. Okay, Kritika, Kartika, sorry. So
Yes, sir.
this is a net reaction. Okay. Now just have a look. Q value of the beta decay will be what? We just in the first class I was showing you know how we calculate the Q value. Q of the reactant minus Q of the product into C square. Right? You remember the very first lecture of Professor Tomar? If not, let me show you. Uh, let me show you. Uh, in this lecture, if you will go, lecture number 3, this was being explained by Professor Tomar that how this Q comes. If there is an alpha particle emission taking place, how do we calculate the Q? Okay. Similarly, into this question, we are calculating the Q now. Okay. So yeah. So Q value will be 12N, which is the reactant, minus 12C star into twice of Me into C square. Okay. Now let's see what is there. 12 is the mass, 931 mega electron volt, minus 12 into 931 plus 4.43 minus 2 into 511 kilo electron volt. Now from where this 511 and this 931 values are coming? For this you have to check the lectures. Example, if I can show you this 511 and 931 values, just a quick recheck. This you have to remember it, that for in beta particle it
Yes,
is
sir.
uh,
Yes, sir, I know the value of C square, and I think this is the electron, right?
exactly. Okay, great. So we put this here, then we calculate, then this calculation it's giving us 11.8767 mega electron volt. So the answer is 11.88 mega electron volt. So the maximum kinetic energy of beta particle will be 11.88 mega electron volt, assuming that neutrinos have a zero energy. We are not considering the neutrinos, they having a zero energy. So the maximum energy will be 11.88 maximum electron volt by the beta particle which is emitted. If you want to note it, you can note it down. Arumugamji, you can note it down, you can try to understand it later, and if you're not able to understand, you can write an email to me or you can WhatsApp me. Kartika, I'm giving you my WhatsApp number also. If you have any problem, you can write me anytime. I'm just putting it in the chat box. Uh, you are able to access my YouTube channel, Kartika, right? And you're able to access the drive, the solutions that I'm giving along with the study matter.
Oh, okay, sir.
Are you able to understand it? I mean, are you able to access it? This is my WhatsApp and this is my email ID. Okay.
Okay, I will note it, sir.
You can note it, and then in case you have any problem you can go through it. The solutions or this PPT also I will be putting in the drive, and my YouTube channel also you is being shared with you people. And today I will share you this book also in the study matter. Into this book, it is by Chemical Liver Text. They have actually explained you have to consider these three chapters now: radioactive decay 1, which is alpha decay, and radioactive decay 2, which is gamma and beta decay. There, Anumugam ji, it is specially for you. If you go to this chapter, I will upload this book. You can go through this book. What is happening in an alpha decay? What is the energetics of alpha decay, and how they are correlated, and then what is happening in a beta decay, and conservation laws that we were talking about right now, and how this mega electron volts are coming, and then Gamma decay, what is the energetics of gamma decay? All this is being explained into this PDF. Then these are the quantum mechanics stuff. These are not of our use right now. Then you have to go through radiation decay part 2. Just a minute. This all has been explained by Professor in the shell model and liquid drop model, if you people remember from the last class. This all have examples of exact what is being asked. So you can go through it if you're not able to understand. Let me show you what we have now. Now we are to the gamma decay. What happens in a gamma decay, and how this gamma decay is calculated, and all these features, that what is a lambda, what is the angular momentum parity, and what is happening in a beta minus decay, beta plus decay, reaction of phenomenology, and what is the changes that are taking place, and what are the conservation laws, and then Fermi's theory of beta decay, matrix element, decay rate, all these being very beautifully explained. Then interaction of radiation with matter in the same way which Professor Tomar is explaining. This is a very good PDF. I will share this time with you people. What is happening when there is a collision? You just have to go through what you have to go through. Just remember it. Let me show you once more. For Arumugam ji, you have to go through just a minute. Let me go to the beginning of this. This is the introduction to applied nuclear physics by Paulo Caparello from MIT. So into this you have to go through introduction of nuclear physics, radioactive decay 1, nuclear structure, and radioactive decay 2. Only these chapter, and you can go through 1, 2, 3 and 4. It has examples and all the basics which will be of your importance. Along with the combined notes, I will be sharing this book also. And if you see the video, if you see this book, if you see the notes, if you see my video, you will be able to at least solve 8 to 9 questions of the assignment. There is nothing outside of that. You just have to read. You just have to give only one day will be enough if you go through the book, and one day for the video. So the whole week classes you can do on Thursday, Friday and Saturday we can discuss. It will be really nice if you people can see the videos from the beginning, then a discussion could be good. Else only I will be speaking and you people will not be able to interact. Anyways, Kartika, you have noted my mobile number and email ID.
Yes, sir. I've noted.
Okay. Okay, now we are going to the solution again. So this is what we have solved. You have noted a solution. Do you want to note it, or you will be able to solve? Hmm?
But sir, I'm sorry, sir. What?
You want to note this, or should we move forward?
Sir, move forward, sir.
Okay. Going to the next question. Again, now we are going for the gamma decay. A stationary nucleus of 24 atomic mass units emits a gamma photon. Okay, now this is emitting a gamma photon. The energy of the emitted photon is 7 mega electron volt. What is the recoil energy of the nucleus? Now there are three things. There is a gamma emission. There we have to calculate the recoiling energy, and we know the energy of the emitted photons. So the energy of the emitted photon is E equal to HF 7 mega electron volt. If you go through the video, you will know why this is HF. Then you will come to know. So please go through the video. Now let's go to the question. So if P be the momentum of the photon and V be the recoil velocity of the nucleus, then by the conservation of momentum, P equal to mv, we know. So from here, E by C equal to mb, or V equal to E by mc. Now the recoil energy is kinetic energy, which is half mb square, which will be m by 2 into E square over m square c square. Why? Because V value we have put it at E by mc, which is E square over 2 mc square. Now this E is given to us as 7 mega electron volts, 2 is the here, mass is given at 24, and c square we know 931.5 electron volt square. So mega electron volt. Now by calculating this, we come to the term 1.1 kilo electron volt, where 1 AMU is 931.5 milli electron volt. This is the answer. I don't know how much it is stable, clear to you. First of all, you have to go through this video from where this equation is coming. This equation is coming from here. If you'll go to the gamma decay equation, no, yeah, here it is, gamma decay. So what is happening in a gamma decay, and what are the selection rules, and then decay scheme, and then yeah, this is gamma decay constant. How this v by c square is coming from here, what happens when there is an absorption, and how do we calculate the tau. If you will go through these videos, you will come to know that what I am trying to say. And this equation is in the beta decay also. Yeah, you can see here how this lambda is correlated to momentum, and this is electronics of beta decay, which I have already explained. Just a minute. Okay, anyways, I'm not able to find it right now. It must be here in this equation. This equation is here only. I'm not able to find out, but in this alpha, beta, or gamma decay, you will find this equation somewhere. So how this question is solved, you can find from here. Kartika, are you able to understand what I'm trying to say? You will have to go through the notes and the videos, then only you will be able to solve it. I cannot explain everything, but we know there is a stationary nucleus which emits a gamma photon whose energy is given to us as 7 mega electron volt. We have to find the relation of recoil energy and the momentum, and in the formula of kinetic energy we directly put the values and then we find out the answer. I will upload this slide. There is one question of this type in the assignment. If you will solve this question, you will be able to solve that question. So this is the answer. Please go through this. I will upload this PPT. Okay, and
Okay.
still if you have problem, please write to me or WhatsApp me. Now let's go to the next question. Similarly, example is saying, this question is saying a nucleus of mass 218 atomic mass units in free state decays to emit an alpha particle. Kinetic energy of the alpha particle emitted is 6.7 mega electron volt. Now they are asking the recoil energy of daughter nucleus. It should be 1.5, 0.25 or 0.125. I am going to the solution directly. Now the conservation of total momentum. What does the conservation of total momentum applies to us? This, that the momentum of the alpha particle and the momentum of the daughter nucleus, the sum of it should be equal to 0. This thing we know, right? That means P1 should be equal to P2, right, Kartika? If we know
Uh,
this, there is a conservation, then the momentum of alpha particle and the momentum of daughter nucleus, it should be same. So P1 plus P2 equal to 0. That means P1 equal to minus P2. This you will agree. Okay.
yes. Okay,
Now
sir.
there is a daughter nucleus of mass 218 atomic mass units. So parent nucleus is 214 atomic mass units. Now it is emitting an alpha particle. So what will be the mass of the daughter nuclei? You tell me now. If there is a parent nuclei, it have a mass of 218 atomic mass units. So what will be the mass of daughter nuclei? 218 minus 4, right? Which is 214 atomic mass units, right? And mass of alpha particle is 4 AMU. Right now we solved some question before, right? Arumugam ji, Kartika, anybody is here?
Yes, sir.
Okay.
Yes, sir. I'm like,
So
before I went to the CT scan program, that's why I'm not able to answer.
okay, no problem. So
I'm the
E,
patient.
E is
Sorry.
a
Okay. Sorry.
E is the energy of the daughter nucleus in mega electron volt, which is given to us as 6.7 mega electron volt. Now we directly put the equation that I already showed Arumugam ji. 6.7 mega electron volt is the energy. P1 square by 2m. which is E equal to P2 square by 2m for daughter nucleus, and this is for alpha particle. Now these two are conserved, right? Dividing the above two equation, we get E over 6.7, E over 6.7 equal to small m by capital M. So from here, E equal to 6.7 into small m by capital M. Small m is the mass of alpha, capital M is the mass of what? Parent nuclei. Sorry, daughter nuclei. So 6.7 cross 4 over 214, the correct answer is 0.125. Kartika, are you able to understand? Again, I am repeating. There is a conservation of angular momentum. We know P1 is a momentum of alpha particle, P2 is a momentum of daughter nucleus. We have a parent nucleus whose atomic mass is given to us as 218 atomic mass unit. So the mass of the daughter nucleus will be what? The mass of the daughter nucleus will be this 214, because 4 atomic mass unit is subtracted from here. So this is the mass of the daughter nucleus and this is the alpha particle. Okay, now we know the equation E equal to P1 square by 2m. For alpha particle, energy is given to us, and for this is the daughter nucleus. Now we divide this equation by this equation. E over 6.7 mega electron volt equal to small m by capital M if we consider P1 equal to P2. Okay, so P1 square equal to P2 square, it will be cancelled out. So E equal to this. Are you able to understand, Kartika?
Yes, sir.
You tell me what happened. Now you explain to me in your terms. Now I'm just showing you the solution. What is happening here? You explain now.
Okay, sir. Here, the total angular momentum of a system is conserved.
Hmm.
So, momentum of the alpha particle
Hmm.
and the momentum of the daughter nucleus is
Yeah.
conserved.
Okay.
Uh, Initially, the parent, sorry, the daughter nucleus, uh, uh, parent nucleus mass of the parent nucleus minus mass of the alpha nucleus gives the mass of the daughter nucleus.
Yes.
So, uh, energy of the daughter nuclei uh, equal to p square by 2m.
Yeah.
This gives the answer. So, substitute the equation, we get the answer, final answer.
Yeah, you're right. But here you made a mistake. We
Yes.
substituted this momentum for both of them. For this, the value was given to us, and this value was asked by us. What is the required energy of the daughter nucleus? So we know then P1 and P2 is equal. If we square it, no, it is negative sign. P1 is square equal to P2 square. So negative will become positive, right? So this,
Okay.
if we divide this by this, these two terms, na, these two terms they will cancel out. Uh,
Okay. 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 Okay, sir.
this
Uh,
and this, they gets cancelled out, and
okay.
this two also cancelled out. Okay, so the
Okay.
correct
Okay.
equation becomes E over 6.7 equal to small m by capital M.
Okay.
Okay, now
Okay, sir.
so you put the values E equal to 6.7 cross small m by capital M, you get the answer. The correct answer is D. Arumugam ji, are you
Oh,
able to understand?
Yes, sir. Yes, sir.
Okay,
I'm
great,
the.
great. Now going to the 10th question. The two 500 kilo electron volt photons created during positron annihilation are emitted at 180 degree. Due to why? Why they should be in opposite direction? You go through the class, you will come to know this is due to the conservation of linear momentum. This is the last lecture. You will come to know about it. One question I left before, which was also there, decay of nuclear isomeric states of ground state is hindered due to what? It is also a part question of your assignment, and the right answer is large spin difference. And for knowing the details, you have to go through the classes. Go through the classes, class number 3 of week 3. You will get the answer how these nuclear isomeric states are related to the ground state and are hindered because of large spin difference, which is delta S, which should be high. No problem, this relation I have already shown you, this how this kinetic energy and momentum relation is coming. Now let's go to the question of this. So in the last class, Professor Tomar has talked about Cherenkov radiation. Who discovered Cherenkov radiation? And I have a question. The charged particles travel faster than light when the Cherenkov radiation passes through water. What is Cherenkov light, and give some application of Cherenkov radiation. Let me show you what he has taught. He has he is taught like this. If we go to the last class, in the last class, Professor Tomar has talked about Cherenkov radiation. So, what are they? Cherenkov radiations. They are the charged particles passing through a transparent dielectric medium with velocity greater than the phase velocity of the light in that medium, which emits an electromagnetic radiation in the UV visible region, which is the Cherenkov radiation. So, the condition is what? The condition for Cherenkov radiation to be emitted is V should be greater than C by N. N is the refractive index of the medium, C by N is the phase velocity of the light in the medium, and it appears bluish white. So, it is very interesting to see. If you put appropriate photomultiplier tube, you can detect the electrons energy electron intensity by means of this Cherenkov detector. So, what exactly happened? What is the mechanism? So, what happens? First of all, the condition for Cherenkov radiation is what? The velocity of the electron has to be more than c by n, which is the phase velocity of the light. C the speed of light, which is universal constant, n is the refractive index. Now, if you see the V by C velocity of the electron upon C velocity of light is called beta, and it becomes beta n greater than 1. So, the condition for Cherenkov radiation is beta n should be more than 1. Now, how can this beta n should be more than 1? The velocity of the ion can be close to C at the most, so it can never be more than the speed of light. Relativistic ion we just now saw, 1 mega electron volt electron has a beta value of 0.94. How can a particle move more than that? So, the light is emitted because of the field leaving behind the ion. It is emitted in a cone, and in this condition it is made of very small time, because once the electron loses energy in the medium, that condition will not be met. So, till that condition is met, which happens in only in the high energy part of the beta, then you will find for that particular time in the initial phase of this journey, it will emit that light, and that light happens to be in the blue region. That is why Cherenkov radiation is having color in blue range. So, this is a typical swimming pool reactor, Apsara U in Mumbai. This one, this one, this is a typical in Cherenkov radiator in Mumbai. And what is this used for? You see the beautiful color in the swimming pool. So, any swimming pool type of reactor, if there is fission taking place, then the fission products are emitting beta particles of high energy, you will see blue light. So, Cherenkov radiation in terms of energy loss is not much, but it is important in terms of beauty of the radiation, the detection of beta by Cherenkov radiation. Okay, so let's see now. I have asked you certain question. What is Cherenkov radiation? Who discovered it? And is it true or false the Cherenkov particles travel faster than light when the Cherenkov radiation passes through water? And what is Cherenkov light? And give some application of Cherenkov radiation. So the answer is like this. Cherenkov radiation is a light produced by charged particles when passed through an optically transparent medium at a speed greater than the speed of light in that medium. We have learned it. Cherenkov radiation was discovered by Alexey Cherenkov, a Soviet physicist. A brief flash of light produced when a particle carrying an electric charge travels faster than light in media such as air and water is known as Cherenkov light. Now, what are the applications? Cherenkov radiation is used in astrophysical experiment to study cosmic showers. In a pool type reactor, the blue glow that I showed you right now, it is used to gauge the radioactivity of spent fuel rods, and it is used to identify the nature of the particle being examined. So, this is the Cherenkov radiation, and that is all for the week 3 classes. So, I would like to ask you now, Kartika and Arumugamji, what have you learned from today's discussion? Just give me a quick feedback, like what did you learn from today's. I will share that book PDF, I'll share the combined notes, I'll share my PPT with you, which will definitely help you. And if you see the video of Professor Tomar, you will be able to solve at least 60, 70 or 80% of the assignment. Some questions are of high level, which I will not help because you have to submit the assignment. And if you are having problem, still you can send me a mail. But now you tell me, what have you learned from today's class? I just want to know that. Then I can wrap up. Kartika, can you tell me what have you learned from today's class? In short, you can tell me.
Yes, sir. It's very useful for me your class.
No, but what did you learn today? What new thing that you learned about today? Were you able to understand what is Sennenkob radiation?
Yes, sir.
Okay,
Sir,
okay.
Okay.
And were you able to understand that what is the energetics of alpha, beta, and gamma decay? How do we calculate the kinetic energy, and how do we solve the numericals?
Yes, sir.
And then were you able to understand other technical terms that has been taught in the class? And I also showed you the solution of certain question of the assignment.
Yes, sir. I can understand, but I want to read more.
Okay, no problem. What about you, Arumugamji? Arumugamji, are you there?
Yes, sir. Yes, sir.
So
I learned today alpha, beta, gamma rays, and first we learn to the solution of the equation. We
uh,
learn about it. Then only we can do for the solution for everything. So I have to learn that things today.
okay. Do you know what is Q value? How do we calculate the Q value? What is the change in kinetic energy we
The
calculate now?
yes, sir, the first question.
Yeah,
Yes,
the
sir.
first question. In fact,
Al-
and then I solved one question of each type. What is happening when there is an alpha decay? What is happening there in beta decay? What is happening when there is in gamma decay? And then what is Cherenkov radiation and other things. So
yes, sir. Yes. Yes.
this was about the weekly classes. So
Okay.
I'm wrapping up, and if you have any problem, you can email me. You can message me, and then we will see.
Sure, sir. Sure, sir. Sure, sir. Sure, sir. I will note the email. Anything I will write.
Okay. Okay then, Kartika, I think I should leave, right? If you have any problem, if you have any doubt, please write to me. Okay. And if I have to improve.
Thank you, sir. Thank you for your classes. Thank you for your classes, sir.
Okay, Kartika, should I leave now? Kartika, are you there? Okay, seems like she has left. So okay, Anumugamji. See you next week. But
Okay, sir. Thank you. Thank you,
please
sir.
try to
Thank you, sir.
see week 4 classes. I'll upload this video and everything. Okay.
Okay, sir. Okay, sir. Sure, I will share, sir. Have
Okay.
a nice day, sir.
Okay, thank you.